All right. Thank you so much, Tyler, for the introduction, and thanks to all of you for being here with us so early in the morning. So I'm Ricardo. Today we're going to talk about test time adaptation. We're going to delve into the problem formulation. We're going to discuss methods and benchmarks. So this is our plan for the day. So we're going to see how we can smoothly move from standard unsupervised domain adaptation to unsupervised test time adaptation. We're going to discuss two different scenarios: the scenario where the test distribution does not change, and the case where the distribution change forever over time. And we're going to draw our conclusions, of course. Generally, we all know that deep learning works, machine learning in general works pretty well in the IID conditions. So if as Tyler said, if the train and test distributions are aligned, but things start to go south if these diverge. So this is the standard training paradigm. We have, so for example, this is a segmentation task. We have some images, some annotation. We throw all of these to a learning algorithm with our favorite model, and we end up with a trained model that we can use at deployment. So what happens? We have our training distribution. Let's say that our model was trained on daylight images from an AD task, and things go sort of well. But as samples start to diverge from the original distribution, things go worse and worse. And you're going to find many ways to define this problem: the dataset bias, the domain shift problem. But let's say that regardless on how you call this problem, there are many formulations that try to address this, from domain adaptation to domain generalization. And here we focus on test time adaptation. So let's see what we mean by that. So many people are familiar with the standard unsupervised domain adaptation formulation. And here we have a model trained on some source distribution, and we want to adapt it to a target distribution for which we only have samples and not labels. And these distributions are separated by the so-called domain gap. And typically adaptation happens offline, which essentially it means we run several epochs over these shuffled data sets, and can be transductive or inductive. What does it mean? So if it's transductive, essentially we adapt and test on the same data. Think about, you have two MRI machines, one on which you perform well, one on which you don't perform so well. And so you want to really improve the performance on these very same data sets. In the inductive case, you see some samples from this target distribution, but you want to generalize to other samples from these different distributions, right? It can be, I don't know, if you have autonomous vehicles, you may want to adapt to a new city, but of course you want to keep working properly on this city, right? Not on just the very samples used for adapt. Now, how do we get similar, more close to the test time case? In the source-free setting, we assume not to have access to the source dataset. So we are given a model and we need to adapt to a target distribution without access to this data. And also in this case, you can be in the transductive or in the inductive setting. Now, what does it mean to do test time adaptation? I think it's very important that we give the proper weight to the words, right? It means we really want to perform well at test time. So also in this case, people assume not to have access to the source data set, and this adaptation can be offline or online. I think there is a little bit of a mess in the detail. So if adaptation happen offline, test time adaptation equals source-free adaptation. There's no difference. But things get, let's say, more complex and, in my opinion, interesting if adaptation happens offline. So you keep adapting to batches of test samples as they come along, and you need to perform properly on these batches of samples, right? And so in this case, test time adaptation really becomes a problem on its own. If we go in this scenario where you happen adaptation happens online, I think it's also interesting to relax the assumption of not being able to access the source dataset, right? Let's assume you're developing methods for self-driving vehicles. probably you can store your source dataset if this makes things easier for the adaptation. Of course, if you if testing adaptation happens offline and you also assume access to the source dataset, this just becomes standard unsupervised domain adaptation. All right, this is what I call, let's say, stationary testing adaptation, which let's say, okay, we move from a source distribution to a target distribution, but the target distribution is fixed. So let's say you have an MRI machine, images from an MRI machine, and you move to a second machine. In continual test-time adaptation, things happen online in the sense that you adapt batch by batch, but the target distribution is time dependent, right? Let's go back to the autonomous driving vehicle. Like in stationary test-time adaptation, you want to adapt to one city, you drive in one city and you adapt, but in continual test-time adaptation, you drive throughout the whole world, right? You see different cities, different weather condition, and this and that, right? It's funny that one anecdote from CVPR last year, I keep making examples related to self-driving vehicles. I spoke with someone from the self-driving industry, and they told me that actually in some countries it's illegal to change your model as the vehicle drives. So probably don't use test-time adaptation on your vehicles, but on other things. All right, just shout out to the first people who worked on this topic. Like as often happens in domain adaptation, we arrive to the problem years after the NLP community. So there are works from the NLP literature from like almost 15 years ago working on this very same topic. Just to mention some problem formulations that may ring a bell, but are slightly different from what we are talking about. So there is a huge body of works focusing on incremental domain adaptation. So in this case, adaptation can be source-free, can be with access to the source dataset, but the idea is that you adapt to different target datasets in different steps. So each new target dataset is, let's say, a learning episode on its own. Instead, in continual testing adaptation, we have a continuous shift, right? And I think it's also worth to mention domain generalization. So what's the difference between test-time adaptation and domain generalization? In domain generalization, you train on your source, and then you test on other datasets, and there's no adaptation, right? So if you take the let's say you take test-time adaptation, the offline case can be seen as, let's say, domain generalization plus adaptation in a way. It's like if I'm doing domain generalization and I have time to do something on the target dataset, this would be test-time adaptation. All right, let's discuss the methods. So to recap, our overall goal is to adapt a given model to new batches of samples. The extreme case is that we want to adapt to a single data point. So this is you see an image from a great benchmark where you have that really posed I think the correct question, right? Do ImageNet models generalize? And the answer was no. ImageNet models do not generalize even to simple corruptions like this is some simple blurring. We can all tell this is a bird, but a standard ImageNet model cannot do that. And so like in test-time adaptation, we say, okay, we're given this sample. What can we do to improve the model on this sample, right? And we're not given any label. So again, another similar, very related literature is that of model robustness, right? And so model robustness, like many literatures don't talk, but model robustness and domain generalization are the same things, right? You train on one distribution and you want to generalize to different distributions. All right, what can we do to do these complex tasks, right? We want to improve at test time. Indeed, some people don't talk about test-time adaptation, but they talk about test-time training, which is, it's cool, right? It's like the learning, is like, Tyler and Joel are going to talk about continual learning, but it's really like, we never stop learning, right? Even at test time. So these are some standard methods. I focused this presentation on, let's say, mainstream approaches. Of course, you can find many different works in the various ICCV, CVPR, ICCV, and if you're interested in these, I encourage you to check out the latest, let's say, free editions of this conference from the past 3 years. So first method, this is a self-training with pseudo labels. What does it mean? It's like I have a model, I can do some prediction, and this is a method from 10 years ago, devised for semi-supervised learning. And it's like, okay, if the prediction are not too bad, let's trust this prediction and let's fine-tune our model on these predictions. And essentially, this encourages models that are on the safe side of the decision boundary, if you think about classification, to move a bit farther away from the decision boundary. And in doing so, you also carry some of the other samples with you. And even though it seems counterintuitive that relearning the model on its own prediction works well, it actually can bring you quite far. And this is a standard baseline in test-time adaptation. And if you check all the possible facets of domain adaptation, this is one of the, let's say, standard regularization terms that people use. Batch norm statistics adaptation. We have a pioneer of this here in the first line. But it's, so what does it mean? It's like, we all know from Machine Learning 101 that you should gather the training statistics of your data set, normalize your data, and apply this normalization to your test samples. Now, 6-7 years ago, people discovered that it's very helpful if you can do this normalization thing throughout the network in different layers, and that's how batch normalization was born. And it's like, but the problem is also in batch normalization, you gather the statistics, let's say the batch norm statistics from your training set, right? And these will not generalize to target distributions. So what Massimiliano and others discover is that it's very beneficial to adapt these statistics throughout your model lifetime, right? You can just keep gathering target statistics, let's say, you do essentially a moving average between the training batch norm statistics and the target statistics. And this works quite well. Then people went deeper into this and they discovered that, let's say, okay, batch norm layers are really cool. You can really go far playing with those. Batch norm learning with pseudo labels is cool. You can go quite far, but there are caveats. So you can just go that far by adapting the batch norm statistics, but on the other end, you go too far by adapting the whole network via self-training with pseudo labels, right? So what researchers discover is that you should do self-training, but just adapt the batch norm parameters. So the scaling parameters. And they did this by not training on pseudo labels, but minimizing the self-entropy of the output. And I mean, if you write it down, it's almost the same thing, except that in pseudo label, you can, let's say, apply more easily some thresholding or so. But the cool thing about this approach is that this can scale to other normalization layers, right? The problem with adapting the batch norm statistics is that modern networks like Transformer have fewer and fewer batch normalization layers. They have more and more layer normalization layers. And in their layer normalization layers, you just use the current test batch statistics. And so with these, you can really just update the rescaling parameters. Self-supervised learning doesn't need a lot of introduction, I guess, but let's say that you craft some ground truth associated to your data by, let's say, I don't know, rotating your images, and the ground truth is the rotation degree, and you need to predict this. But anyways, what people can do, if you see on the title here, they call it test-time training, not test-time adaptation, but it's the same thing. If you treat each new batch as a self-supervised learning problem, you can improve the performance of your network, right? It's like going back to Tyler's intro, it's like you bring your test batch closer to the comfort zone of your model. And one note is that people discover that self-supervised learning also helps as a pre-training in terms of model robustness. And of course, the first thing you want to do is to have the strongest possible model, right? That's the best thing you can do. Then you want to do test-time adaptation, but that's the last resort. Another cool method builds on data augmentation techniques. So what people discovered is that, like, test time, we have one batch. Is like we're used to learn from 1 million samples. Now we have to learn from one batch. So what we can do is really apply a lot of random augmentations to this batch, then take the original model's prediction and minimize the entropy on those. So it's like, I'm sorry we don't have a whiteboard, but it's really helpful if you think about like a classification. You have a decision boundary, and like the batches that are, let's say, that you can hope to improve on are the ones that are, close to the decision boundary, but already slightly on the safe side, right? And maybe it can be that the particular condition of this sample is brings the sample too much closer to the decision boundary or on the other side. But maybe if you apply a lot of augmentations, you create, let's say, a cloud of points around the decision boundaries, but more of these copies are on the safe side. And so if you do pseudo labeling or entropy minimization, you can really bring them to your side, right? So benchmarks, in general, you can apply test-time adaptation wherever you like, right? But what people are doing are, let's say, taking data sets from the model robustness literature. So you train on one data set and you adapt on corrupted version of this data set, like you train on ImageNet and you adapt to ImageNet C, or you take a data set separated by a domain gap, like these ImageNet A and ImageNet R are versions of ImageNet. By version of ImageNet, I mean the same 1000 classes, but they are gathered taking different sampling strategies. Even though there are even benchmarks, like we have ImageNet V2, where they follow the very same sampling strategy and still you have a performance gap. So you can really benefit from test time adaptation in most situations. The only constraint is that the set of classes needs to be the same. So Tyler and Jota are going to talk about continual learning, and I guess Simas talk about zero-shot learning. We're going to talk about new categories. Here, adaptation means overcoming domain shift. So it's the same set of classes, right? You can potentially have new classes, but you cannot improve on those. So you better have just the same set of classes that you saw at training. This is what you can check the papers if you're interested in the numbers, but this is what you can expect, right? ImageNet C, you can go up to, let's say, reducing the error of 22%, which is quite a bit. But also something that I'd like to show you is on ImageNet A. So ImageNet A is really a adversarial version of ImageNet. It doesn't mean it was perturbed with adversarial samples. It means that it was taken with a sampling selection mechanism that was maximizing the fact that the samples are hard for the current model. And in this case, results do not improve much. So it means test time adaptation has its limit. So let's move to continual test time adaptation. We have focused on, when I talk about stationary distribution, I mean, I take an ImageNet model and I adapt to ImageNet C, but that's it, right? I'm not moving away from this data set. In continual test time adaptation, we keep adapting our model as the distribution changes. And we have an additional challenge here. We're going to hear a lot about this, I guess, later on, but it's catastrophic forgetting, which is I forget important cues that were helping my model to classify on samples from the source distribution. So let me show a little bit also of what we did with my collaborators. Is in 1 year ago, 1.5 years ago, there was a lack of benchmarks to test continual test time adaptation on semantic segmentation. So what we did was introducing a benchmark called Oasis, online adaptation for semantic image segmentation. And just, yeah, to, again, on the literature uses many names, like 1 year and a half ago, it didn't even feel a good idea to call this as test-time adaptation, and we call this online adaptation, but this is test-time adaptation. So here we have to do image adaptation in sequences of temporally correlated frame. So it's like, think about a robot exploring this room, and it needs to adapt sample by sample. And we devise, let's say, yeah, I'm very biased in defining what I did as fair and realistic, but what we thought is a fair and realistic pre-train, validate, and deploy pipeline. And a dataset where catastrophic forgetting is an issue. So first stage, the model is trained offline on your dataset. And again, we want to stress that it's really important to start from a strong model, right? But this is generally true for domain generalization and domain adaptation. Just if you start from a model that does random chance performance, you're not going to adapt properly. If you have a model that does, I don't know, I'm making up numbers, but let's say 80%, you can think about going to 90 and 100. But if you have a model that is really weak, adaptation will not work. So that's why it's really important to have a pre-training phase. And then we propose a validation phase where through a simulator, we have different sequences of samples. So I didn't say this, but we focus on AD scenarios. So like semantic segmentation of urban scenes. And we validate the adaptation algorithm at end on these different validation sequences. And then just the best model, so not cheating on the test set, we transfer the test-time adaptation algorithm on the final test set, which are, let's say, real sequences with different real-world domain shifts. Baselines we apply are the ones we discussed, right? Self-training with pseudo-labels, batch norm statistics adaptation, and batch norm parameters adaptation, self-supervised training. So the main problem, like often happens in continual learning, is catastrophic forgetting. I'm not going to talk much myself about this, but let me tell you how it shows up in test-time adaptation. So in semantic segmentation, we divide categories into stuff and things. So stuff are like the road, the sky, and the, yeah, stuff that you cannot count, and things are the things that you can count, like cars, pedestrians, and so on. And what happens is that there is a, let's say, the distribution is really, there's much more stuff than things. So what will happen if you keep adapting blindly your model is that you'll forget about things in favor of stuff. So you can see a sequence here. So you have a non-adapted baseline in the center and a continually adapted method using using pseudo labeling adaptation here. And as you can see, frame by frame is just forgetting about cars and other things, right? There are no more poles, and you see how the non-adapted baseline is much better than the continually adapted one. And yeah, I guess it's not forgetting car because there are a lot of them, but it's forgetting about signs, poles, and these things. So what can we do? One thing we can do is what we call naive learning, and sometimes in the literature is called as episodic learning. So it's like a frame is an adaptation problem. So you're given a frame, you adapt to it, and then you move on, and you always restart from the original model, right? So this is not great because we work with robots, and I can tell you something, you cannot afford to adapt frame by frame, right? The frame rate is too high to do that. So you really want to adapt to one every n frames, and you want to keep building on your knowledge, right? So something that works well is keeping an episodic memory. So you keep assuming access to the source dataset, and you use this as a regularization term. So you do adaptation, but you also keep optimizing your source training loss. Another thing that works well is reset strategies. So it's like somewhere in between continual learning and naive learning, which is like, if I have some indicator suggesting that I'm forgetting, I reset to my θ0 model. If not, I keep learning. How we evaluate, we compute MIOU on each frame, and then we average across the sequence and average across the dataset. Well, check the paper if you're interested, but really spend quite some time on the pre-training. And this is what we are analyzing, right? We analyze sequences, not just final numbers on the tables, right? And yeah, again, some numbers. And here you can show that without adaptation, things go poorly. But if you adapt without regularization on the bottom, you're going to forget about things. Now, sorry for the table full of numbers. So I just want to tell you like what you can expect from this. So relative performance, the maximum we could achieve is like something close to 9% on a fair validation, on a fair evaluation on the test set. And the standard deviation is pretty high. So like in some cases, you can see that maybe the improvement is 2%, but the standard deviation is like 6. So it means in many sequences you did worse. And something that it's really important to assess and that people are not doing much in the literature is additional computation overhead. We're doing test time adaptation. In some cases, it's all right that maybe you do 100 iterations on your test set. If your test set are like medical images, right? You have time. But if it's a robot exploring the real world, you cannot apply an algorithm that needs to process each test batch for 100 iterations. Cool. So just this is funny. There were last year at CVPR, we had 2 very similar contemporary papers. So I'm just going to discuss also the other papers that was published at CVPR last year. And they propose a more complex and fancy method that's essentially you keep a moving average between the source model and the target model. But something that I was very happy to see is that also in this case, these researchers resorted to a sort of reset. So it was nice to see that in parallel, we reached a similar, let's say, conclusion from the methodological perspective. Yeah, just check the papers for the number. And we focus on 2D tasks here, but mostly for the speaker comfort zone, because that's what I work on. But there are papers doing online adaptation. I've mentioned NLP, but this is a computer vision conference. So computer vision wise, you can see as Massimiliano did online adaptation for robot kitting. There are some pioneering work also for depth estimation and for more recently from for 3D LiDAR segmentation. Something that like I want to mention is that again, I don't like when similar literatures that are addressing one similar issue don't talk to each other. And in this case, I wanted to mention test time augmentation because I really think it's very similar. So what is it, test time augmentation? This is something that in the earlier ImageNet challenges, I think test time augmentation was part of the standard pipeline, right? You were not just evaluating on the whole image. You were taking, I don't know, like 20 random props and you were averaging your predictions, which maybe people still do. I don't know. But anyways, that's the simplest way of test time augmentation, right? You have a fixed set of augmentation, you apply them at test time and you average. But you can do fancier things, right? You can have a RL agent that, given a sample, predicts the augmentation that you should do. It could be like something that if the brightness is low, it will increase the brightness. And I'd love to see more on this, and this can be applied to test time adaptation, right? All right, we're incredibly on time. So conclusions, test time adaptation, recent and active area. So check out all the ICCV, CVPR news proceedings. If you're interested in these, you can find probably 4 to 5 papers for each conference in the past 2 to 3 years. But the roots are from very well-established fields, right? So let's not reinvent the wheels. people in NLP have been working on these problems for like 15 years. So let's look at those. The continual learning counterpart introduces additional challenges like catastrophic forgetting, and evaluation itself can be an issue, right? Okay, so I'm not gonna go through the references, just since we're gonna release the slides, you can check the references that I keep for myself. But there, as in many literature, you can find some awesome Testtime adaptation GitHub repos, so check them out because they're most likely more complete than my reference list. Thank you so much to my collaborators. They're like 90% are here, so thank you also in person, I guess. Yeah, thanks to all of you.
You know what the microphone is?
No.
Okay.
Yeah, thank you. So we can get started. So raise your hand and I will help you.
Thank you. So, Jerry, you mentioned they type picture. So before applying adaptation, what are some methods to determine how much the test images differ from your training institution?
Yeah, so I guess the question is how we can, let's say, at least predict how bad it will perform, right? So that's a great point. And again, we're talking about literatures not talking to each other. And there are whole body of works focusing on OD detection, miscalibration detection, miscalibration. And so the short question is that there are methods doing so, like checking the entropy of the output, the maximum softmax of the output. Many metrics are similar to the ones that we optimize when we do Testtime adaptation, but I've not seen, can be my ignorance of course, many works that first check how badly we perform and then decide whether to adapt or not, or just provide a safety measure. Yeah.
Thank you.
Any other questions? Thanks very much for learning all about stuff like that. Really helps. I was wondering, correctly, you said that one is offline to the standard communication, so on online. Talk about robots, which we will both, I guess. Right, if you get standardization and sort of the next robot, or the next robot, is there like a Google or academic always for them?
So yeah, that's a great point. I guess the question is, can the offline methods and the online ones talk to each other for robotics? So I guess it depends by your application, right? Let's say that I'm selling robots and these robots need to be deployed into a specific warehouse. And if I know the warehouse, so what I do is not Testtime adaptation. I'd go there, acquire some data, and do standard offline adaptation. I would even do some semi-supervised domain adaptation because often a few labels are quite cheap to obtain. And instead, you cannot apply these concepts. For example, if I'm selling robots for houses, like private properties, I cannot go there to acquire data set a priori. So I really need the things to adapt on the fly, right? Because I don't know the environment. Yeah.
You always want to start with a good model, right?
Yeah. I guess it all depends on the how unpredictable the environment is.
So ICCV training.
Yeah.
We are stored on this queue and retention formulations.
All right. And it all depends on how predictable the environment is, right? Because if you know what the target environment will be, often like, I'm sorry to say this in an adaptation tutorial, but I would just annotate some samples and you can go with just tiny amount of samples much farther than any unsupervised domain adaptation algorithm, right? But as the uncertainty increases more and more about where it's going to be deployed, like this cannot be applied for urban environments because the whole world is too large to have annotations from every city and time of the day and so on. So in those cases, you go to the more to the online case.
Great, thank you.
Thank you.
Thank you for the great talk. I have a really good question. So you were mentioning about that supervised path, and that seems like the terminology. So that's something it's test-time training. I was wondering whether the differences test-time training and test-time adaptation, or if there is any at all.
So the question is if there is a difference between test-time adaptation and test-time training, and no, I don't think so.
Cool, and then I saw you were evaluating, you were like the benchmarks showing in the segmentation table where if there was A5 and then they were and so there is also corruption data sets for segmentation benchmarks like local and cityscapes, local statistics. Do you think that would also be that as evaluation benchmark?
So yeah, that's a great point. Like, why didn't we use more data sets for like with a corrupted version of segmentation data sets? We could have done it. So essentially, yeah, I confirmed that what we did was pre-training on GTA5, validating on Cynthia, and then deploying on the test set of ACDC, so Snow, Night, Rain, and Fog. And we could have done it. It was an arbitrary choice, right? Even with just this amount of data, we had to like, let's say that the GPUs ran for quite a bit. So we could have ran more sequences, but it was just, yeah, very arbitrary and let's say budget discussion.
Yeah, great, thanks.
Thank you.
Okay, I'll ask.
Yeah, look forward to that.
Thank you for your report. So, I will start off question about the since you just mentioned that it's time beginning and adaptation is maybe one and the same thing. So every time if the model is adapting on this, and it's also going to show that because every time new it is constant, the model is adapting to it and read it. So how do we tackle this problem? Because while the motivation behind the case is very solid, we also kind of raise this article concern that the model will also be taking a lot of time and doing it. And the second question is that how do you also decide the stopping criteria? Like where and when do you stop the model from learning or not?
Okay, yeah. Related to how we can decide when to stop to adapt. So yeah, we thought a lot about that. Let's say in the continual test-time adaptation case, you never want to stop because the world keeps changing, and so you keep on adapt, right? But the problem is that at some point you diverge too much from your original model θ0, and so you want to, or at least that's our solution and the solution from this other research group, to reset the model parameters back to the factory weights. And so it's not really about stopping, but it's more about, let's say, yeah, resetting in this case. And instead, for what concerns, let's say what was, sorry, can you repeat the first part of the question?
So, I mean, the inference time is also going to rise.
Okay, yeah, I remember now. Yeah, so about the inference time, what's the trade-off, right, between the amount of iterations and the, yes. So that, as I mentioned before, it depends what you gotta do, right? Because if you have an agent that needs to work in real time, then like what they called as the episodic way of doing test-time adaptation. So I receive a sample, I adapt, evaluate, and then I move on, and maybe I reset to the original model, cannot scale. So you need to find a trade-off between the, let's say, how much you learn and how quickly you want to move, right? So like probably you're gonna have like, okay, I'm gonna run a few adaptation iterations every n frames. But in that case, you cannot reset all the time the model back to the θ0 factory weights, right? Because otherwise you just adapt, you work with the adapted model, just one every n frames, and on the other you have the original model. So it's a delicate trade-off. Yeah.
So my other thing was not so that how value is because it's out of the cycle number of the equation.
All right. Well, when to stop adapting? It's a trade-off again between you're minimizing a risk, right? You're minimizing a loss. So you can either go at convergence if you have time, but again, if you're focusing on real-time applications, then when to stop will be, let's say, it's not up to you, it's just up to how far you can move, right? So the only thing you can do is say, okay, I'm gonna run one adaptation iteration every n frames, and I hope that's enough. Or I need to, work on how fast the algorithm is. Sorry, that's not a great answer. I don't have a clear answer for this.
Thank you for the great question. Thank you,
Thank you all.